Welcome to a deep sea odyssey where we dive into the heart of tragic OceanGate incident. In this series, we will explore possible scientific perspectives behind this event, a quest for understanding that embraces curiosity and knowledge. These videos are educational in nature, shedding light on potential factors while acknowledging that the definitive truth lies in post-incident investigations. Guided by science, we will dissect hydrodynamics, material science, and more. What's our goal? To unveil hidden truths, to decode the forces that shaped the OceanGate tragedy. The deep sea environment is complex as it involves a combination of many factors. The main ones to consider in the design of an underwater structures are hydrostatic pressure, temperature, seawater, biological effects, and pollutants. These factors can be studied separately, but it must be kept in mind that they always act in combination. So there exists a complex interaction among these which cannot be ignored. Hydrostatic pressure is directly proportional to the depth. So as you go deeper, the hydrostatic pressure will keep on increasing. So according to one of the expression, it can be given by this equation where P is the hydrostatic pressure and H is the depth where you are in the sea. This is the main mechanical loading on the composite structure, although other static and dynamic loads should also be considered, which I will discuss later on. Density of seawater is another factor, and it depends on various parameters including pressure, salinity, and temperature. Seawater is slightly compressible, so the level of ocean would rise by about 30 meters if it was not the case. So pressure has the largest influence out of the three over the range of possible variations. For example, increasing the pressure from 1 bar to 1000 bar increases the seawater density by 4%. If salinity were to go from 0 to 40 grams per kilogram of seawater, density would increase by 3%, while it would also increase by 1% for a temperature drop from 40 degrees Celsius to 0 degrees Celsius. So overall, pressure has the largest influence on the seawater density. Finally, underwater structures are subjected to loading by ocean currents. These can be very fast in certain areas, but tend to decrease near the seafloor. Their influence can be reduced by the knowledge of the immersion site for fixed structures and careful hydrodynamic design. There are a number of models available in the literature to estimate current velocity at certain depth. One simplest current model used in offshore structure world is given as this equation, where U current is the current velocity at elevation Z, where Z varies from the depth until the zero, which is the mean sea level. UC naught in the equation is current velocity at mean sea level in meters per second. Z is the vertical coordinate which measures the depth where you are and with reference to the mean sea level. And finally, D is the water depth, so wherever you are measuring it from. So this is how you really compute the current velocity if you really want to account for that in your design. Composites have been used underwater for many years. The main industries concerned today are oceanography, military, and offshore oil and gas. For all these applications, the principal manufacturing technique today is filament winding, which enables cylindrical tubes to be manufactured in a semi-continuous process at low cost. These images show a schematic of the process, while the other images of the actual machine and process. Nowadays, impregnated band of fibers are commonly used to simplify the process as shown in the image. Conventionally, as you can see, you had fibers and it has to go through resin impregnation process, and then it was wound together in a cylindrical or any shape. While nowadays, to eliminate this step, they use already impregnated fibers, as you can see on the right hand side image. One of the early uses of these materials was for instrumentation housing. Filament mount reinforced epoxy cylinders such as those shown in this image have been used in the past. Another application for deep ocean exploration is in submersibles or DSVs. For example, here you can see Nautile, if I'm pronouncing it correct. They make use of composites but not for the pressure chamber. which is metallic for all manned vessels. All the yellow fairings is glass reinforced composite, but the main pressure vessel housing for the crew of 3 is titanium alloy sphere. For some unmanned submersibles, composites are used for pressure resistant hulls, especially for those which are autonomous. 2 examples are AutoSub and Advanced Unmanned Search System AUSS. And design of the former began in 1988 for the UK Natural Environment Research Council, and extensive system development took place over 5 years, and the first complete vehicle was built between 1995 and 1996. AutoSub undertook its first autonomous mission in July 1996. It is 7 meters long and has depth limit of 1600 meters, which is around 1.6 kilometers. The AUSS vehicle developed for the US Navy in the 1980s, as you can see on the screen, and was designed to operate down to a depth of 6 kilometers. It is 5 meters long, 0.58 meters in diameter, and weighs 1.2 tons. The center section is a cylindrical carbon epoxy pressure hull, wound at 0 and 90 degrees with titanium hemisphere regal ends. Another area where composite materials are of interest is in offshore structures. So one structure for which there has been considerable development work is composite risers. The design requirements for this application include a 150 year of fatigue life. So you can see the level of conservatism, and which is 10 times the service life. So if your service life in this case is 15 years, so you should design your structure for a fatigue life of 150 years. The connection between the tubes is critical. Titanium alloy end fittings are favored generally, and that was used in case of OceanGate as well. However, how they were connected is another topic, and we will cover that later on. Each prototype tubes required 5 days of filament winding. So you see a very rigorous process, and it takes a very long time, tedious process in my opinion. And more than 680 kilogram of carbon fibers were used. So an internal titanium liner was employed to facilitate the water tightness and to simplify the connection with end fittings. So I don't know about OceanGate if they had this kind of titanium liner. Generally, you don't use composites directly. You will always have some kind of reinforcement which are metallic in nature, and again, people have to look into that. There are always certification societies, so whatever you are designing, you always have to get it certified from different standards and design codes, and DNV is one of them. So for subsea operations and things, so you can find for composite risers, you can find DNV document, which is DNV RP F202, and this discusses about the composite risers which are in the subsea environment. These are some of the figures of typical subsea risers, and you can see it's not really only used of composites, but you can see it has laminate layers, but there are many other things involved. In some cases there are metal structures or reinforcements there as well, which have different purposes. So your design has to be really thorough, since these are very critical components and require a lot of careful considerations. Today, so what I have shown you today we have embarked on a journey that has unraveled the complexities of this aquatic realm, showcasing the delicate balance between challenge and ingenuity, and I hope you can sense the pulse of excitement. This tale has just begun, so the plot thickens as we dive deeper, immersing ourselves in the realm of deep sea vectors. So join me as we decode the impact of pressure on water absorption, decipher the symphony of composite mechanics, and bear witness to the rigorous testing that is required to see the potential use of composites in underwater applications. So my fellow adventurers, keep your senses tuned and your curiosity alive. The upcoming videos promises an exhilarating ride filled with insights and groundbreaking revelations. Subscribe now to my channel to become a part of this thrilling journey. So see you in the next episode.